All right, we've done our algebraic review. We know what a square root is. We know how to simplify radical expressions. We know how to solve quadratics, and then we also know how to handle proportions. We know how to cross multiply, or if you like, form product of means, product of extremes, set them equal, and then solve out. That means that we have the algebraic background we need to begin to discuss similar polygons, and that is the topic of the chapter. And the next chapter really is also about similar polygons. We will begin to talk in particular about right triangles, but all the results there will ultimately follow from what we have discovered about similarity. So let's begin. And of course, what I owe you initially is a definition. I'll begin with a rough idea, and then in a moment I'll offer the precise definition, the one, of course, I would expect you to give on the exam. Here then is the rough idea, and I'll compare this to congruence. Two figures are congruent, we said, if they have the same size and shape. That was the rough idea. Now let us say that two figures are similar if they have the same shape. So notice that we've removed one of the requirements. Congruence was same size and shape. Similarity is simply same shape. So we remove the requirement of same size. Let's have a picture to illustrate this. I have three triangles in front of you. If you can see the color, the interior one is red, the middle one is green, the outer one is blue. These are similar, let us say. They certainly look like it. Now, let us ask, what precisely does this mean about angles that correspond, and what does it mean about sides that correspond? Well, what it means about angles that correspond is that they are the same. So for instance, let's pick a set of angles that correspond. And what would be a good color for this? How about purple? So if we were to pick a set of angles that correspond, like lower left corner, they would all have to be equal to one another. If we were to pick another set that correspond, like top, they would have to be equal to one another, and so on. Okay, so similarity means that angles are equal. Now what does similarity mean about sides? Well, obviously it doesn't mean equality of sides that correspond, because if it did, we would have the same size, but that's not a requirement. Instead, what we have is proportionality, okay? And we know what proportionality is. We have talked about that in our algebraic review. So here then is our precise definition of similar for polygons. Two polygons are similar if angles which correspond are equal and sides which correspond are proportional. And what does proportionality mean? Well, let me remind you. Pick a pair of sides that correspond, form their ratio. Pick another pair of sides that correspond, form their ratio. Those ratios are equal. That's what proportionality is. It is equality of ratios. So again, to say that the sides of two similar polygons are proportional means that the ratios of sides that correspond are all equal. Here's an example. Of course, it would be good to have a picture. So we have a triangle ABC and a triangle RST. Notice first that the angles of ABC are equal to those of RST. In particular, angle A equals angle R, B is equal to S, and C is equal to T. And notice as well that sides are proportional. So for instance, if we were to take the ratio of AB over RS, that is 2.2 over 3.3, and then take the ratio of BC to ST, that is 1.8 to 2.7, and then finally the ratio of AC to RT, that is 2.4 to 3.6, those all have the same value. And what is that value? They're all equal to simply 2 over 3. Okay, so angles are equal and sides are proportional. Now, we need to have a symbol for similarity, of course, just as we had a symbol for congruence. Nobody wants to have to write out is similar to every time they wish to say that two polygons are similar. Our symbol for similarity is simply the tilde, as you see up top. Okay, so if we wish to write a similarity statement, we'd have something like this. Triangle ABC is similar to triangle RST. Okay, so there it is again, the similarity symbol. Now, we know from congruence that when you write our study of congruence, that when you write a congruent statement like triangle ABC is congruent to triangle RST, the order of letters matters. And letters in the same position correspond to one another, so that tells you what sides and angles are equal. The same is true with similarity. If I say that triangle ABC is similar to triangle triangle RST, this means that A corresponds to R, B corresponds to C, and B corresponds to S, and C corresponds to T, because those letters are in the same position. And that then will tell me what angles are equal, and it will also tell me what sides are proportional. Okay, so once we have this basic idea, we can solve some simple problems. Here's one that isn't really very difficult to solve at all. So I have a triangle ABC and a triangle RST, and let us say that they are similar to one another. I give you that information. And it should be clear what corresponds to what. A corresponds to S because the angles there are equal. R corresponds to B because, again, the angles are equal. And finally, C corresponds to D. And we know what similarity means for sides. It means that sides that correspond are proportional. And we know what that means. Proportionality is equality of ratios. So what we do is write ratios of sides that correspond and set them equal. Okay, so let's see. Let me ask the question, to what does X correspond? X, of course, is from triangle RST. To what does X correspond in triangle ABC? Well, notice that X is opposite the angle with the single hash. So it corresponds to the side opposite the angle with the single hash in triangle ABC. So that, of course, is 4. So the X corresponds to 4. So what do we do with sides that correspond? We form their ratio. And then we do it again. So let us pick another pair of sides that correspond. Okay, well, I could try the 12 from triangle RST. And note this as well. The X, which is the top of the first ratio, is taken from triangle RST. So the top of my second ratio also must be a side taken from RST. We could try the 12. To what does the 12 correspond? Well, the 12 corresponds to the Y because the 12 is opposite. Oops, let me clean that up. The 12 is opposite the single hash angle, the double hash angle. And likewise, the y is opposite the double hash angle. So I could write that x over 4 is equal to 12 over y, but notice that that equation, of course, has two variables. So let me pick again. Okay, so let me pick the 8 instead. Well, to what does the 8 correspond? Well, 8 is the side opposite the triple hash angle. In triangle ABC, the side opposite the triple hash angle is 6. So that's our proportion right there. And I won't take the time to solve that out. Of course, you can do this. It's a very simple proportion, and it will give you the value for x. Now, we can also solve for the value of y. Okay, so I tell you what, I'll start a ratio with y. Okay, and that means that the second ratio in my proportion will also need to be a side taken from ABC. We have to be consistent about that. So let's see, to what does y correspond? As noted before, the y corresponds to the 12. They're both opposite a double hash angle. And then let's see, let me go back to triangle ABC for the top of my second ratio. So I'll pick the 6 because we know that that corresponds to the 8. And then once again, I have a proportion that I can solve out. Okay, so proportionality of sides in similar triangles allows you to solve in certain cases for unknown side lengths. All right, now let me talk about scale factor. This is another way to discuss the relationship of sides that correspond in similar triangles. Okay, so here's the story. So assume that triangle ABC is similar to triangle RST. We know that means that sides that correspond are proportional. So let's set the proportions up in this way. So we know that RS over AB is equal to ST over BC is equal to RT over AC. And of course, we know this because letters that are in the same position correspond. And notice, for instance, that RS, which is first, second in triangle RST, then would have to correspond to AB in triangle ABC because RS and AB are both first, second. Okay, so there's the extended proportion that we can set up because triangle ABC is similar to triangle RST. Now, when we say that these ratios are equal, we mean, of course, that there is some number that they all equal, okay, some constant value that each of them equals. Let us call that k. You might wonder why I wish to say this, but you'll see in a moment. So what this really means is that RS over AB, ST over BC, RT over AC, they're all equal to the same quantity k, because, of course, they're all equal to one another. And let's do just a little bit of algebra with those three equations. So take the first of those and multiply both sides by AB. Take the second, multiply both sides by BC. Take the third, multiply both sides by AC, and you'll get the result that you see. Perhaps I'll do one of these with you. So we have RS over AB is equal to K. I'll give myself a little bit of room here. Let me multiply both sides by AB. Okay. And then on the left-hand side, I have an AB over AB, which becomes simply 1, and then I get RS is K times AB. Okay, and also ST is K times BC and RT is K times AC. Now let's think about what this really means. What this really means is this, is that when we have a pair of similar polygons, then for some constant K, some number, whatever it happens to be, each side of one is K times the side of the other to which it corresponds. And this number K is the scale factor. So again, if we have a pair of similar polygons, then as we go from one to the other, each side of the other is some constant K times the side of the first to which it corresponds. Okay, so let's look at a particular example. Let's find the scale factor as we move, in this case, from left to right. Okay, so we know, for instance, that the 2.2 and the 3.3 correspond, not of course because they're both on the left-hand side, but rather they're both opposite the angle with 3 hashes. Okay, so what that means is this, is that as we move from left to right, we multiply we multiply the 2.2 by some constant k to get the 3.3. Okay? And we can simply solve for k then, divide both sides by 2.2, and then that means that k is 3.3 over 2.2, which is the same as simply 3, 2, 2. Okay, so that's the scale factor as we go from left to right. That is, as we move from a side to which it corresponds in the second triangle, in each of those cases we multiply by 3 halves. Okay, it's the same constant factor in every case. Now, if we were to consider the scale factor as we go from right to left, well, I won't take you through the details of this, but I think it'll come as no surprise. And I'll call this K prime to distinguish it from the K we saw before. If we go from right to left, it will be the reciprocal of the scale factor when we go from left to right. Okay, but again, the point here is this, is that similarity implies that there exists a single quantity, a single constant quantity, such that when we multiply each of the sides in the first of the similar triangles, we get the length of the side to which it corresponds in the second. Okay. That is the introduction to similarity, so you now know what the definition is. You know that it means equality of angles that correspond, proportionality of sides that correspond, and we know that this is ultimately equivalent to talk of a single constant scale factor for the two triangles.